let's look at some common student misconceptions in this unit, atomic structure. Looking at the keywords, the first two include element and atom. Let's relook at them together. So atom is the smallest unit of any element that still has the properties of that element. So let's take it with an example. Smallest unit of any element, let's say gold. A gold atom will have all the properties of the element gold. What is an element then? Well, element is a pure substance made up of only one type of atom, nothing else. So element gold is made of only gold atoms, which cannot be broken down into simpler substances by chemical reactions. Well, we know an atom can be broken down to subatomic particles, electrons, protons, and neutrons, but those subatomic particles don't exhibit the properties of the element. Only an atom can exhibit the properties of an element. Next up are nucleons and electrons. Nucleons, as the name suggests, they are the particles inside the nucleus. So in the center of the atom, the space is called as nucleus, which include the nucleons, which are protons and neutrons. So protons are the positively charged particles, however neutrons do not have any charge, and they all get clustered together in a tiny space, a very compact structure in the center of the atom. The rest of the atom is a huge empty space which is occupied by electrons. Electrons are found in different energy levels. We'll take up in details in one of the next videos. The next up are atomic number, mass number, and isotopes. So atomic number that is represented by the letter Z is actually the number of protons. Well, in a neutral atom, number of protons and number of electrons are equal. But what's so important about atomic number is that this is what identifies an element. On a periodic table, the elements are listed from 1 to 118 on the basis of their atomic number. If the atomic number changes, the identity of the element changes. Mass number, represented by letter A, is the number of nucleons. So nucleons, which include protons plus neutrons. So the total particles present in the nucleus describes the mass number, and it is always a whole number. Remember, protons are particles, neutrons are particles. They can be just 1, 2, 3, 4. They cannot be 1.5. They cannot be half. Isotopes. Different elements can exist in different forms on the basis of difference in the number of neutrons. Since number of protons are the identity of an element, they are going to remain same. If number of protons are same, number of electrons will also be same for an element. But what can change is the number of neutrons. When the number of neutrons change, the mass number changes, which gives rise to different isotopes of an element. So remember, isotopes, they have the same atomic number, but a different mass number. They have the same number of protons and electrons, but the different number of neutrons. Let's analyze our first statement and figure out if it's a myth or a fact. Mass number can be a decimal as seen on a periodic table. What do you think? Write your answer in comment before I reveal it in the video further. What do we see in the periodic table? Let's zoom in further. Okay, we have focused now on two elements. Mass number, can it be a decimal as what we see on the periodic table? Not exactly. The number on top left corner in the periodic table is not the mass number. It is the average atomic mass, or we can call it relative atomic mass. So what's the difference in mass number and relative atomic mass? Well, we know for each element there can be several isotopes existing, and isotopes differ in their mass number. Based on the natural abundance of each isotope, we can calculate an average atomic mass, and that is what is represented on the periodic table. Because mass number is the sum of protons and neutrons, now either an element can have 1 neutron or 2 neutron or 10 neutron, cannot have 2.5 neutrons. That's not possible. Neutron is a particle, and thus it can only be in whole number. There cannot be half of it. This is why mass number is always a whole number and never a decimal. What you see on periodic table is the average atomic mass. Let's solve this exam style question which most students struggle in. The data here shows the naturally occurring isotopes of carbon and their relative abundance. So we have 3 isotopes of carbon in the data, carbon 12, 13, and 14. The mass is given, so carbon 12 has mass of 12 and its abundance is 98.90%. For carbon 13 it's 13 mass and 1.09% abundance. For carbon 14 the mass is 14 and abundance is 0.01%. What we have to find out in this is the average atomic mass of carbon and see if it matches with what is listed on periodic table. Let's do that. What we are going to do is we are going to calculate the average atomic mass by taking into account the abundance percentage. So we multiply the percentage with the mass number and we add all of them together. So 98.9% 0.09% times 12 plus 1.09% times 13 plus 0.01% times 14, and we put the values in calculator, and this gives us the average atomic mass of carbon as 12.011 AMU, which does match what is given on the periodic table. So in this way, using the data, we can always calculate the average atomic mass of any element. Another exam style question for this topic is like that. Chlorine exists in two isotope forms naturally, chlorine 35 and chlorine 37. The relative atomic mass of chlorine is 35.5, which is what is listed on periodic table. What does this tell you about the relative abundance of the two naturally occurring isotopes of chlorine? Let's go back to the previous slide and decode this. So over here we see that the most abundant isotope is carbon 12. It is 98.90%. The average atomic mass comes out to be 12.011. So we can see the average atomic mass comes out to be a number closer to the most abundant isotope. Let's apply this analogy to the next question again. Over here, the average atomic mass of chlorine is 35.5. Now this number is closer to chlorine 35 or chlorine 37? Well, clearly it is closer to 35. This tells us chlorine 35 is relatively more abundant than the other isotope chlorine 37. So we are going to say, since atomic mass is closer to mass number 35, hence we conclude chlorine 35 is more abundant. Next, we'll analyze another statement to find out if it's a myth or a fact. Different isotopes of the same element react differently. Let's look at the statement. Different isotopes. So for carbon, it can be carbon 12, carbon 13, carbon 14. That means they have same proton number but different neutron number. If proton number are same, number of electrons should be same. So different isotopes have same number of electrons. Element react differently. To react, element uses its electrons. So only electrons affect the chemical reactivity of a substance. Protons don't participate in chemical reactions. Neutrons have got nothing to do with it. So let's look at some data to find some evidence to figure out if this statement is correct or not. Here we have data for carbon isotopes. Look at the orange column clearly. The chemical properties of all the isotopes are same, right? And why they are same? Because the number of electrons are same in all these isotopes. But if you look further down the table, the physical mass of carbon 12 is lightest and carbon 14 is heaviest. The density is different, rate of diffusion and henceforth are different. So we can see the physical properties vary, but the chemical properties remain the same. So what do you think? Is the statement a myth or a fact? Yes, you got this right. This is a myth. The fact is that isotopes, they have identical electron arrangements, so they have identical chemical properties. Only the physical properties may differ. But the question is, how is this isotopic mass and the relative abundance actually measured? Would one go to the whole word and see all the carbon present in the word and find out which one is carbon 12, 13 or 14 and how much percentage each isotope is present? Clearly not. That's pretty impractical. So what do? Well, we use mass spectrometer. Let's see how. So in a mass spectrometer, we take a sample and then we bombard the sample with highly charged particle to make positive ions of the same. These ions are then accelerated through a charged field where they get deflected. So when the positive ions, they pass through a negatively charged field, they get deflected. Now the lighter particle is going to be deflected more than the heavier particle. And once they are deflected, they are detected that how many are getting deflected further or closer to the charge plate. In this way, we figure out, we count these deflected particles, and here we get a graph where the relative abundance is plotted versus mass by charge ratio. So in this case, you see 28 is the lighter isotope and 30 is the heavier isotope. Now it depends upon which isotope is deflected most will be related to a taller peak and greater relative abundance in nature. So in this way, we can now find out of a given sample what was the mix of isotope, and we correlate it with its natural presence, and in this way we can find the relative atomic mass of any given sample. Okay, another analysis statement is, if the tallest peak is always the molecular ion or the heaviest isotope. Let's see further. So the tallest peak, let's go back to the previous slide. The tallest peak is this. Do you think it's the heaviest isotope? No, it's 28. So what does the height of the peak indicate? Well, the height of the peak only indicates its relative abundance, right? So what do you think about this statement? Is the tallest peak the heaviest isotope? Clearly not. It's a myth. Tallest peak is called as the base peak, and it represents the most abundant isotope, which is not necessarily going to be heaviest of all. It varies from the element to element. The molecular ion peak is the one at the highest m by z value, which is definitely the heaviest isotope, but it can be small or big. It is going to vary with the data we have. Let's apply this on an exam style question. So in this question, we are given the mass spectrum of element X with 3 peaks at 24, 25, and 26, and their relative intensity. What we have to find out is the relative abundance of each isotope and then the relative atomic mass. Now, in this case, if we add up all the intensities, 79 plus 10 plus 11, we get 100. That means the relative intensity is already given in percentages. So we know the X24 isotope is 79% abundant, X25 is 10% abundant, and X26 is 11% abundant. So we got the relative abundance. Now let's apply it to the formula to calculate the relative atomic mass. So we take the percentages and times it with the mass. So 24 times 79% plus 25 times 10% plus 26 times 11%, plug all the values in the calculator, and you get 24.32 AMU as the relative atomic mass. Okay, another exam style question of this topic is this. A beam of electrons, so remember electrons are negatively charged particles, are passing close to a highly negatively charged plate. So there's a negatively charged plate and the negative electrons are passing through it. What's going to happen? Negative are going to repel, right? And that's what is given in the question. When the electrons pass close to the plate, they are deflected away from the plate. So these electrons which are coming, they are deflected away from the plate. All right, we understand the question. Let's see what the question is asking us to do. What would you expect if the experiment is repeated with protons, the positive particles, or neutrons? Let's sketch the image to make it simpler for us. So if we are going to make the image for electrons, we see the electron beam which was coming. As it approaches the negatively charged plate, it's deflected away from the plate. Okay, now we are going to sketch the same for positively charged protons and the neutral charged neutrons. Here we go. As we know, protons are positively charged. So when they come close to the negatively charged plate, it's going to attract it, and the deflection is going to be towards the plate. For neutrons, they are neither going to be attracted nor repelled. They are going to pass straight without any deflection. So here is how you write precise yet complete answer for the Cambridge style questions. Further, they are asking which subatomic particle would deviate the most. So in this case, the comparison is between electrons and protons. Since protons, they are of opposite charge, they are going to be strongly attracted toward the negatively charged plate, and hence they are likely to be deflected more as compared to the electrons. Another exam style question from this topic is this. So if you're given any element or any ion, you can be asked for its mass number, atomic number, number of electrons, protons, neutrons, any of them. So we are going to practice a couple of them. Feel free to pause the video wherever you want and solve these questions in your notebook, write your answers in the comments, and then proceed further in the video to check your answers. This is going to help you better prepare for the exam. Let's go. Let's solve the first one together. So for vanadium, the mass number is 51 and atomic number is 23. We know the symbol is V by using the periodic table. And then on the top left side as a superscript, we write 51, which is the mass number. And bottom left side as a subscript, we write atomic number, which is 23 in this case. Now, atomic number is always equal to proton number, which is equal to electron number since it's a neutral atom. So number of electrons are going to be 23. And to find the number of neutrons, we are going to subtract the atomic number from the mass number. So 51 minus 23 is 28. Let's check all the answers. So pause the video again and self-assess your answers to see if you got them all right. Okay, another set of questions is when instead of neutral atom, ions are given to you. So in this case, you are given a potassium ion, which is a positively charged ion. So how are we going to find the number of electron? Well, we are going to look up for the atomic number, which is 19. So we know the number of electrons in a neutral atom would have been 90. Now, since it's not an atom, it's an ion, that means one electron is out of it. Look at this carefully. When the sign is positive on the ion, in the calculation we use a negative. So a positive ion has given out the electron. So out of the normal 19, one is out, and hence the number of electrons left in this ion are 18. So here are a few more questions for you to solve. Pause the video, solve the questions, and then look up for the answer. All right, here's the answer key. With this, you have got atomic structure concepts all in place. So now practice past paper from Cambridge and self-assess your knowledge. If you're stuck at any question, remember, you ask, I explain.